It's my great pleasure to welcome Professor Yifei Mo from the University of Maryland here for our department colloquium today. Let me briefly introduce Yifei. So Yifei obtained his PhD from the University of Wisconsin Madison and then went for a postdoc to MIT. And that is in fact where the two of us first met. As a nice anecdote, it was actually Yifei who interviewed me. So without him, I would not have gotten my postdoc position there. And so things that could have turned out quite differently. In 2014, I think, Yifei then joined the University of Maryland for 2013. He received the Outstanding Young Scientist Award there from the Maryland Academy of Science in 2019. And in 2021, he was recognized as a highly cited researcher in the top 0.1% by the Web of Science. And I was not surprised that Yifei's work is well cited because he has essentially pioneered the first principles modeling of solid-state batteries. And that is what we are going to hear about today. So we will now see his presentation, Computation, Accelerated Design and Discovery of Novel Materials for Next Generation Batteries. Now, we switch over to your presentation. All right.
Okay, thank you, Alex. Good afternoon, everyone. It's truly an honor to be here, right? So actually speaking humble, I did not interview him. I just actually coordinated this interview. So, you know, we obviously look at the job and it's glad to know so we're here and meeting a lot of wonderful colleagues here. Yeah, so yeah, basically today, you know, what I'm going to do in my presentation is introduce my research over the past couple years, how we use first principle computation, right, including machine learning, that help to accelerate design and discovery of new materials for next generation battery. So I'm from material science engineering department, and I realize a lot of students here are chemical engineering, right? So you guys will be interfacing with materials right down the line in the career. But I will make sure my talk is accessible to you. So if you look at the history of modern materials development, you will see that any materials, right, from the inventing the laboratory to the commercialization often takes decades. Usually it's 2 decades, right? For example, the lithium battery that's so ubiquitous in each of your cell phone and even electric vehicles. The concept is very well demonstrated in the lab in the early 70s, but the commercialization, really comes in the 90s. So you guys probably heard about this Materials Genome, right? Materials Genome initiative launched by back then President Barack Obama. And basically, the idea is that we need to have a way, right? That's discover, develop, and deploy new materials much faster, so we can accelerate this innovation. That can address a lot of challenges we are facing today, right? So even in chemical engineering, you need to. In a lot of applications we do are limited by the materials, the critical materials. So in our research, because we are a computation group, we are thinking, right, how we can leverage these computation techniques that can accelerate this material design, right? How we can use computers to do that better. So to just give you chemical students a little bit background, right? So this is what Paul Dirac says back in the early 20th century. Basically, he says all these fundamental laws that governs the materials, right? We can say are known, right? Because essentially we know all materials are made of atoms, right? There's electrons. So essentially, what are the physical laws governing the electrons is the quantum mechanical theory, right? And Walter only have a contribution, called a density function of 3, but basically what it helps is that, right, for given materials, you can actually make these quantum mechanical equations solvable. So by leveraging supercomputers right nowadays, with any atomic structure, you can get their properties. So that's what we're going to talk about today, right? Is that how we can use this first principle approach, right? Like just from the atom structure of materials and combining quantum mechanical calculation to understand atomistic level mechanism, right? For example, and how we can have design principles to guide this new materials design, and even more, right? How we can predict new materials on computers. And I would also want to show you guys that because these density functional theory calculations are very ubiquitous and accessible nowadays, you can actually essentially down that a lot of materials, for example, all known materials, and put that in the database. And then furthermore, you can actually leverage this database to achieve this goal. So I'm also going to show you some example of that. Okay, because as a chemical engineering student, right, you need to learn some, at least work with materials in some aspect. Okay, so my talk is about lithium battery, right? So you guys know how battery works, but if we really goes to the materials level, this is sort of how it looks like. Okay, so anode is essentially a graphite, right, forming these carbon layers, and you'll have lithium ion cells sitting within the layer. Okay, cathode is a lithium cobalt oxide, okay, also forming these layers. Okay, these are cobalt oxide layers, and then you have electrolyte in the middle. And during the discharging of the battery, okay, I guess because of zoom lag, the video doesn't show very well. But basically, during the discharge of the battery, like you basically have these lithium ions deleted from de-intercalate, right? What we say from this graphite layer, and then you can see they insert into these cobalt oxide layers. Then lithium pass through here, right? Electron actually pass through the external circuit. That's where you get the power. When you discharge your battery, right, you basically have an exact reverse process. Where the lithium ion is intercalated from these metal oxide layers, right, and reinsert into graphite layers. Okay, so essentially you have these are active materials, right? Because you can see the host lithium, right, host the energy, and in electrolyte in the middle, you can see it's merely a material that transport the lithium and block electron, right? So electron goes to external circuit, so you can harness that current, for your usage. So there are a lot of battery research, right, including cathode and anode. Yeah, a lot of great work happening here on Columbia. It's become a more and more problem that actually this electrolyte is a great limiting factor, because you probably heard all these news about the battery safety issue, right, electrical vehicles, etc. This is because this electrolyte, they are organic solvent that's are highly flammable. And also this electrolyte has a limited stability, which is actually also a problem, because, right, if you want to improve your electrode, right, for higher energy density material, right, that holds more heat and more energy, they often have a stability issue comes in, that's limited your, you improve other component of the battery. So here is the sort of next generation battery, at least one of the most promising candidates, right? You probably hear a lot about the bus. It's called an all solid state or solid state battery. But the key idea is that to replace this liquid electrolyte, right, which is flammable, into a ceramic membrane. Okay, and as you guys saw, right, many of the ceramics they are non-flammable, so you intrinsically improve your safety, and also you can use higher energy density electrode materials such as lithium metal, maybe higher voltage cathode, right? You can pack more energy into your electrode. Yeah, there's also a lot of other advantage. But certainly the problem is that, right, once you replace a liquid into a solid in the middle, as you guys know, right, solid don't transport atoms as fast, right, as liquid or gas. Okay. So there's actually very limited number of solid electron materials that can exhibit this high ionic conductivity. We have liquid electrolyte, and also there are other type of stability, right, such as electrochemical stability, or air moisture stability, which you need for manufacturing, are also lacking. So currently, there's actually no single solid electrolyte that actually satisfy all these, property criteria that's needed. So that's create the needs to develop, new solid electrolyte material system. So that's basically, how our work is motivated. Okay, so we basically gonna use first-principle computation and data-driven techniques to help design and discover new materials. Okay, so here basically shows a chart of the ionic conductivity, okay, at room temperature, right? This is a log scale. And all these materials that are known to the human being, right? That's our conducting lithium. So the dashed line here is a liquid electrolyte, right? Using a commercial lithium battery. So the number is about 10 to minus 2 siemens per centimeter, right? So it's 10 millisiemens per centimeter. So if you compare that, right? Even if you drop 1 order of magnitude, you can see there's only a handful of materials that can compete with current liquid electrolyte. Right? So indeed, in solid, such high ionic conductivity is a very rare and exceptional property. Okay, right? But certainly that's one of the critical property, right? That's limits your solid state battery application. So I guess, yeah, if you look at this material, right, let's say whether we can find some trend or some insight, so we can come up with that material. Right, so you can sort of see, okay, from the chemistry point of view, we have some chemists, right? So those are mostly phosphate, right? PS4, and this geodide, we have garnet oxide, right? You have nitride, hydride here, some other oxide, and here's hydrogen, right? So you basically have all kinds of chemistry. And if you look at the composition, right, they have all these kind of big long composition, because a lot of these material have it though, right, to optimize them. If you look at structure, right, yeah, this one LGPS, yeah, this kind of crystal structure, right, which is a very complex one. This geodide also have its own structure. This is the garnet structure, right? The atoms arrangement look like this. And this is Massican, discovered by Professor Goodenough, right? Who also invented the cathode materials. This is the peroxide, right? So yeah, if you look at those, it's just yeah, a lot of different chemistry, composition, and crystal structures, right? So it's very hard to, obviously figure out who's the best. So I guess for us, the key question is that what really enabled this, what we call super-ionic conductor, right? I think like originally it's called a fast ion conductor, right? But I guess once they got they call it super. Okay, it's not superconductor, right? And then, yeah, then once we understand how can we discover a new lithium conductor. Okay, so just a little bit of materials basics. I know the chemical engineering take transport, right? But I actually, yeah. So sorry, the animation has a serious lag, so it's not showing properly. Yeah, but basically, this is how the atom migration, diffusion happens to solid. It's basically right. The ion sort of vibrates around their crystal side, and then they jump to the next equilibrium side. Yeah. So then the conductivity, right, is usually governed by this equation. So you can see two critical parameters here. One is the activation energy, essentially represents, the barrier, right, when they jump to the side to the other. So certainly the lower is better, right, especially this has the exponential factor. And then the other one is the carrier concentration, right, essentially, it's the lithium, is how many lithium ions can move at the same time. So the higher number is the better, okay? So, yeah, so certainly basically the thing is like in typical solid, this barrier is high, right, and this number is low. And in this LGPS material, right, this is a compound that will be shown as our best performing. This is sulfide. The crystal structure looks like this. Okay, so the green stuff is the lithium. This is basically how the atoms are arranged. Right? The purple stuff is the phosphate, and the yellow is the sulfur. Okay, so basically this lithium, right, sitting in the structure with a nearby, sulfur ion combination. Yeah, then these ions actually form in a structure that are close to a body center cubic system, right? Then lithium actually sees coordinating with 4 sulfurs. Right, okay, so BCC support, then lithium sits here. Sorry, the map is actually very, they remove through this, and the barrier is about 0.15 eV, right, which is very low migration barrier. Yeah, but if you have FCC, right, close packed ions packing, right, which is very common, then they go these paths, and that give you about 0.5 eV barrier, right? So if actually this entering into the exponential here, you know, at room temperature, that difference is about 4 orders of magnitude, right? So, you know, that's a very significant difference. Okay, so yeah, then so you know, then what we do is that then we also use ignition molecular dynamics to see, you know, how the ion diffusion mechanism really works in these fast performing materials, right? Because all these other good super-ionic conductor does not have this body-centered cubic packing, right? So this lithium garnet structure, you know, the lithium actually have this tetra, tetra kind of local environment, and this is you know, sort of animation from our initial MD simulation, right? Yeah, because it's freezing, so you cannot see. But basically, yeah, different from the animation before is that, yeah, before you have this single lithium jumping, right? But actually, if you look at these super-ionic conductors, they have multiple ions jumping at the same time. You know, yeah, you know, so which we think is a mechanism we call a concerted migration, right? Multiple ions jump at the same time, and actually this gives a lower energy barrier, right? So as we, you know, evaluate more using DFT an energy barrier, right? In this, if you have actually 5 lithium moving together, you would only have this low barrier of 0.26 eV. Yeah, but if you only have 1 lithium ion moving, it has a barrier of about 0.6 eV. Right, so similarly, in this Mexican material, we find this 2 ion, you know, jumping together mechanism, right, give you a low barrier of 0.26 eV. But if you only 1 ion jumping, the barrier is actually as high as 0.5 eV. So this is actually counterintuitive, right? Is that, you know, you have an ion going through the barrier, you know, when you have 1 going the barrier, right, it's actually have a higher barrier than you know, have multiple of them going through together, right? Because you would imagine this would be higher, right, because you have multiple ions overcoming the barrier. So we think this might be a key, you know, into understanding why these few materials, right, can give you such unique and exceptional, you know, low barrier for migration and high conductivity. Then we build a very simple physics model, try to understand that, right? So basically, you have this energy profile, right? For example, given by your equilibrium side of lithium, right? So normally, you will expect lithium just sitting at the bottom here. And if you actually closely examine this super-ionic conductor, you will find actually this is from DFT, right? Basically, on this side, it's actually sitting on the top of energy profile. Okay, so basically, right, in this material, you will also have lithium ions there. You may think, right, why would they sit there? It's basically because lithium is an ion, right? It's a plus charge, so they repulse each other. So as a result of this repulsion, you know, this lithium ion is pushed here, and they can actually be equilibrium staying there. So once you have this unique, you know, how do you say, lithium configuration in this super-ionic conductor, you know, then we can evaluate this barrier, right? So we actually take the barrier the same as lithium garnet, right, about 0.6 eV. So you basically would think, right, if you have only 1 lithium ion migrating, right, the barrier you need to overcome is 0.6 eV. And we find when actually if you have this kind of ion arrangement and they have interaction, repulsion between them, the migration is really that the 4 ion migrate together, you know, and then as a result of this multi-ion migration, the barrier is actually increased to the 0.3 eV. Okay, like that's 4 ion moving together, right? Only have 0.3 eV, a lower barrier. So yeah, if you can see the animation, it's probably much easier for you to see why is that the case, right? It's basically, this is probably too small, but basically, right, when you have these ions climbing the hill, right, they're overcoming 0.6 barrier, but these ions at the top, right, they're actually moving down here at the same time, right? So these ions, they're going down here, so they actually cancel the barrier you need a climbing bond by the other atoms. So as a result, you have more ion moving, right? But actually the barrier is lower. So we think that's, how we understand, why this concerted migration mechanism in lithium conductor produce such a low barrier because of this high energy side occupancy, right? That's have a canceling effect, okay, on the energy barrier. So with that, I think this gives a good understanding, right? So you keep a solid, basically, you have ions jump from one side to the other, and you have this high barrier. In super-ionic conductor, right? Usually they have ions occupy both high side and the low side, and when they migrate, right, they have this concerted migration mechanism, right? So these move down while this climbing the hill, and these have some canceling that gives a lower barrier, right? So so with that, I think we have a very good physical understanding, of why these certain classes of materials work so well, right? Like give such low barrier and give a high conductivity. I guess, right? That's just how typically we do the material research, right? Like we observe some phenomena, right? Then we build a simple physics model, right? And from there, right, we build some insight, right? We build a mechanism, so we understand them. I guess the next question is, right? Then with this physical insight, how can we really identify a material, right? Let's say, or predict a new material, right? Let's can do this thing, and give you high ionic conductivity that you would need in solid state battery. Okay, so that's what we're going to show you next, is that how we can identify new materials and structure that use such a quasi diffusion mechanism. Okay, so so we can still do that, right? Let's say the typical high throughput computation approach. But I guess today, I'm just going to show another story, right, where we use a machine learning type of methods to do this discovery. Okay, because machine learning is such a hot topic nowadays, right? And let's see whether it can, provide some unique advantage. Okay. So there's like a lot of machine learning materials discovery paper in the literature. They often based on this principle, right? So first, you should train a machine learning model. And how you train a machine learning model is that you basically want a model to capture the structure property relationship of materials, right? Okay, the structure basically is a crystal structure I showed you, right? Like basically how the atoms arrange themselves. And the property certainly is it can be ion conductivity and activation energy, right? So you basically want the machine learning model, right? You want to train a model that understand this mapping. So how you usually do that, right? That you have a provided materials data, right? We know the structure, and let's say for some of them we also know the property, right? The labor, and then you train the machine learning model to have this mapping. That's called a supervised learning technique, right? It's a one class of machine learning technique. So if you do that, right? Once you get a machine learning model, right? It's showing this black box, okay, right? And this works as a black box. Right? So basically, then you can apply it to a lot of new materials. You can use that to evaluate new materials, and this will give you a property, right? And you just see, okay, whether this property, is good, right? What do we want? So that's how a lot of paper have done for the discovery. But actually, there's a serious issue with this approach. I would say challenges in this approach is that this would rely on you have the good training data, right? That you can, through the training the machine learning model can correctly learn this physical mapping from structure to property. Okay, right? But in materials example, your data that are available to you is often very, very limited. Okay, right? So you guys remember the map I showed you initially, right? If you look at map, it's probably only like 20, 30 materials, right? That we have good connectivity data. And I would say, especially in the materials case, we're really looking for those exceptional material, right? Like those, few materials that just give you such unique property, so you can leverage them for engineering. So that's create a big problem that you have very limited amount of data, right? Like, a dozen, right? Like tens of points. And the good example is even less, right? You probably have a few. And also another issue is that the materials, the poor property data you also don't have. The reason is that the property is so full, no one bothered to measure it and report it, right? So, people know it's bad, but it's, you cannot find it bad. And also, another thing with the materials experiment is that, you guys are experimenting, usually the property measurement have a big variance. For conductivity, it can easily be like plus minus order of magnitude, right? This also creates an issue, especially if I limit the amount of data, because your machine learning, gonna pick up those errors, right, and give you maybe a non-optimal prediction. So I would say that's a big challenge in applying machine learning for materials discovery, right, at least at current stage. Then we what we do this is a collaboration with the Toyota Research Institute, North America and Michigan. Then the alternative approach, what we do is that we switch this how do you say a target problem, right, or mindset, right? Instead of learning the structure property relationship, which have very little data to learn, we say, okay, if we know a bunch of good material, right, can we actually find the similarity among the good material? Okay, if we can find the similarity, then we can say, okay, we can find more material that are similar to this good material, right? Once we find more that are similar, then we can use more accurate first principle calculation, to evaluate whether they're really good. Okay, so with that, I think we bypass two issues, right? So we don't need to worry about we have a large number of labeled data, right? We can just apply this to any data. Another thing is that, right, we also don't need to rely on whether the machine learning model is accurate enough because, we use more accurate first principle calculation to evaluate that. Okay, then how you find the similarity among materials? Right? If you look at all these structure, right, like how the atoms arrange, I think a lot of people have looked at it, right, for many years, right? You probably, I would say by a human it's very hard, right? I mean, you can probably, have some features to do that. Yeah, so how machine learning can help us? And you guys know the similarity for looking similarity approach is called a class 2 method in machine learning, right? It's called unsupervised learning. Yeah, so basically we still need a descriptor, right, that we can evaluate the materials. And for the materials, people here probably know that, right, how people characterize the materials is through the diffraction pattern, right? Okay, like X-ray diffraction or electron neutron diffraction. So we basically borrow that idea and we say, right, we basically computer, we can generate a diffraction pattern and then use that, right, which people know is the effective descriptor of material structure. So here basically we only need it for ion, right? Because as I showed at the beginning, ion packing, this has a big impact on lithium diffusion. But basically here shows that, right, you can compare this lithium sulfide for HCC example, these two to the hexagonal close packing example, and these two to the PCC and the packing, right? You can clearly show that the ion packing, right, can be very effectively identified by this ion X-ray diffraction pattern. Okay. Yeah. So with that, then we can basically perform this unsupervised learning, and then we basically did it on all lithium ion containing materials, right? We just basically just do the ion framework, right? That is XRD pattern, right, generated by computer, and then just do unsupervised learning, to class them together. And we can see that, right? You can see this sort of the data looks like each line is a diffraction pattern, right? But basically, you sort of see they're sort of organizing into a few groups. Okay. Yeah. Then we can what we do now, we organize these groups. These are different way to plot them. Right? This is basically a dendrogram. Basically, it's a tree structure. Yeah. Each tree has a bottom, right? The one material, right? So the two next to each other is that actually deem them to be most similar, right? Then the branch of the subgroup is that they're similar, and and form each groups. Okay. Yeah. So basically, all these lithium containing material are classified into 7 groups, and for each group, right? For each material, then we look at whether there's already known lithium property, right? Because that's for experiments, and we plot it as a color bar down here. So basically, the red color is high conductivity, right? Is what we want, and the colder color is low conductivity. And basically, what we find very interesting is that, right, this unsupervised learning, they can really indeed, classify these good materials and cluster them into these two groups, okay, group 5 and group 6. Right, so you can see within group 5, we have this peroxide, iodide, beta, lithium phosphate, okay, and the lithium, right? So all that color here. On the 6, you have LGPS, right? You know, this phosphate carbonate, lithium nitride, and this the other phosphate, right? So yeah, basically that tells you, using this very simple approach, we can indeed find those good materials are similar, right? Which is hard to do by a human, right? But simple machine learning algorithm uncover that. Then we can move to the next step, right? Is that in these good groups, we still have a lot of other material that are similar to this good material, right? Given by the algorithm, but their conductivity property are not known. Okay. Then what we do next is that take each of the materials and then just run through a initial molecular dynamic simulation and and get the ionic activity data. Okay, so here sort of shows the final results. The y-axis is the room temperature conductivity, right? The value I showed earlier. This is in a log scale, and the x-axis is activation energy. So basically, we want the conductivity to be high and activation to be low, right? So we want the material to be upper left corner. Yeah, and among all these materials that in the group, we actually find 16 of them, have larger than 10 to minus 3 room temperature conductivity, right? You can basically see, they are all sort of highly concentrated on the upper left corner. And for these open squares, right, that's basically the materials that are before that we know ionic conductivity, right? So they are much more sporadic, with lower conductivity and high activation. And with this collaboration, we are also able to generate a lot of new materials, right, that are of interest to the debating data. Okay. Yeah. So with that. Yeah, and there's also experimental confirmation, right? So this is a material, lithium tantalum silicate. So its crystal structure looks like this. This material is known, but it has never been studied for lithium diffusion. Okay, so if you just feed this original material to initial molecular dynamics, you find activation high and conductivity low. Okay, but basically, if you analyze the structure more, right, you actually find there's more lithium side that can create more lithium diffusion channel. Basically, what we did is sort of as we showed in the initial case, right, is that we basically find that if they have this higher energy side but not occupied, then we basically dope these materials, to actually add lithium to the higher energy side. And once that is added, right, we basically activate this concerted migration mechanism that I showed you before. And that actually gives very high ionic conductivity and a lower activation energy. Okay, so yeah, that's sort of a structure that we uncovered by our algorithm, and also they use our physical insight design principle, right, to just on target to improve that. So this is computational lab. This is experiments done by our collaborator Harim Chen and Georgia Tech. Yeah, but basically you also see that the original material is very full down here. And for the doped one, they cannot dope as high as we wanted, but basically you can see high on the conductivity, right, and a low activation. Basically, it's a material, right, that's really discovered, by computation and then improved by computation, and then confirmed in experiments. So that's a successful example. Okay. Yeah. So with that, yeah, I guess another thing is this machine learning algorithm seems to work so well that covers the new material, right, that we want. I guess the thing is through this process, right, can we actually really identify some physical insight, right? Among these, right, because the material similar, you are not known. Yeah, but now machine learning tell you they are similar, right? So what you can cover from this? Okay, so we also did some physical analysis, but I guess for the sake of time, probably I just skip that. Okay, cool. Yeah. Okay. Yeah. So with that, I will move to the second part of my talk, which is material stability, right? Because as we talked at the beginning, one thing with the solid electrolyte is the ionic conductivity. Another thing the stability, because I think the one big topic in the battery nowadays is actually use lithium metal to replace graphite, right? Because you can see lithium metal can pack lithium so densely, so that's a way to significantly improve the energy density of the battery. Yeah, so lithium metal has a lot of problem with the liquid electrolyte, or the solid electrolyte actually, we also face similar challenge, right? Because the lithium metal is very, very reducing. Okay, it's probably the most. Yeah, I think it's the most reducing alkali metal. So they indeed, are incompatible reactive with a lot of materials, right? Even as stable as oxide or fluoride. And another issue is that you have a dendrite formation, right? Okay. So I guess our question is that, right, if you are working with such cases, right, how would you identify or pick a material, right, that are stable with such strong reducing environment, right? I guess like for the chemical engineering students, this is also very relevant to you, right? Because later when you go to the engineering practice, right, you do face the issue that, when you pick a material, right, in a highly reducing or other kind of condition, right, how I pick the right material. So at least, if I want to improve the material, which direction we should go. So actually the computation, as I will show you, will actually offer a lot of insight. The approach we do is that actually we use this materials data approach, database, right, that I shown you, because the DFT computation, right, you can simply perform it on all known materials, right? And once you have it on all materials and you put in a database, that enables you to do a lot of things. Okay, so for example, I would say at least, right, once you know all the energy, you can construct a phase diagram, right? And we can, also predict materials phase stability, right? How materials stability change over, chemical potential, right, environment. And so, okay, so I think Alex is an expert on this, right? So he probably educated you guys a lot on this. So I will skip the technical details and just go to the result, right? So the first thing is I would say is what materials chemistry, right? What materials are stable against lithium metal. Okay, so you actually pull the phase diagram from the materials database, right? That's usually, just like say for lithium or aluminum oxide, that's usually how to use that. Okay. These things are required to be read by material students. So I guess for you guys here is that basically lithium metal is at the corner here, right? This basically gives all the composition in the map. But basically all these in that forms a line, what we call a timeline with lithium, are those stable with lithium, right? So basically among this space here, only lithium oxide and this lithium aluminum alloy are stable, are thermodynamically stable with lithium metal. Okay. So if you use anything like lithium aluminum oxide, right? Basically what will happen is that, if you put with lithium, right, you're gonna have a reaction sort of going through this line, okay? And eventually it's become these two, because that's the only two phase that can be stable with lithium. Okay, and with computation, we can also evaluate, what's stable, and we also evaluate because that's what with the reaction products, right? And we can also evaluate what the reaction energy would be, right? So that's giving the driving force. Okay, so then with this, because you basically have everything in the database, then you can basically just look through different materials, right? Let's say here, we just change the ions, right? Okay, for the sulfur, fluoride, and nitride. Basically, for the sulfide, you basically see still these two guys. Fluoride also these two guys. Okay, people often think fluoride is more stable, it's a very stable material, right? But it's actually not necessarily. And what we find very interesting is that it's actually nitride, right? Okay. Some materials people know is a hard ceramic, right? And sometimes also used for coating. In instruction materials, right? But basically, they are thermodynamically stable with lithium, right? This lithium nitride and this aluminum nitride. Okay, so this is something we can people often don't think about, right? Because when you work on materials, you just work on existing materials. But right, by searching through the database, it's actually very handy for us to uncover, right? This nitride, even with metal cation, are stable with lithium. Okay, so we find that new chemistry class there was more in that, right? You can also, from this database, you can learn, what are the cations you can work with, okay? So here, I call it differently. Basically, it's a ternary compound with a cation, right? So now I change the cation. And the different color is different ion chemistry. And the y-axis is a cathodic limit. Basically means that 0 is stable with lithium, right? Negative is also, more stable with lithium. Right? Positive, you are reduced as a higher voltage. But basically, you can sort of see, right, for oxide, most of them are not stable, but some are stable, right? These are like these rare earth elements, so yeah, so that's why kind of like a lot of good oxide solid electrolyte use a lot of rare earths. And if you see sulfide, none of them are stable. Okay. Fluoride is also not stable, right? Okay, so people often think fluoride are super stable material, but actually they're used as a conversion cathode, right? So actually they're not stable with lithium metal. And if you look at nitride, you can see actually a large number of them are stable with lithium metal. Okay, guys, so this is like, how you can leverage this material space, right? To quickly find the materials that are, stable. At least, from this, what you actually go, right? Like what pattern you use in different chemistry, things like that. Okay. Yeah. So then this is also another way to summarize it in a way that's opposed, in ion chemistry and also with different cation, right? But basically, as I said, you can sort of see like nitride is really this very unique and special material, right? That are stable with lithium metal. Oxide, right? You have to sort of work with some of the rare earth elements. Okay. Sulfide have a narrow window, right? So actually, in sulfide for battery, they have to work with a coating material, on the cathode anode side to protect it, right? Which actually add the complexity and the engineering cost. And I would say another interesting thing we find is the chloride material, which is also a new class of material, how you say, recently, actually 2018, right? Sort of revived by Panasonic, and the solid electrolyte, right? But basically, you see they also have very good cathode stability, but still lack the lithium metal stability. Yeah, anyway, but basically, I hope we provided an example that how you can use database to, improve, right, the materials choice and help you guide the materials design decisions. Okay. The other thing I also want to talk about is the moisture stability, because I feel that's also one of the material stability that are highly relevant to chemical engineers, right? In your, let's say, a lot of your future applications. Okay. So here, why this moisture stability is relevant in solid state battery is mostly because the sulfide materials, solid electrolyte, they are very, very humid sensitive. So basically, if you expose it to, air, right, those steel phosphate material, they basically instantly goes thin. The whole room actually goes thin, almost instantly. And even if you put them in a glove box, right, it actually goes thin, in days time or weeks time. Okay, so which actually is really challenging to work with, right, in real manufacturing. Toyota basically trying to commercialize those material, basically, right, because you have to really have like very high grade driving, to do that kind of thing. Because otherwise, if the driving force is too big, right, usually they have some degradation, and you don't want that. Okay. So here's basically, our computation study to guide on that part. But how we use that, right? So we Alex probably also showed you guys before, right? For moisture stability, what is the thing we can use a diagram? Here it actually goes a bit simple, we just, because this is like all the reaction in the air, right? So basically we just put this reaction, forming this more stable oxide and just, put the gassing species of water and hydrogen sulfide, right, at a certain condition. Then we can basically have a common benchmark for all the material, right? For the same benchmark. Then this will give an indicator of what's good and what's bad. Okay. So then basically we use this energy as an indicator, right? So basically the higher is more stable, lower is more moisture sensitive. Okay. So this is a binary compound without lithium, right? Basically it's in the triangle like this. And if you look at the ternary compounds, lithium and sulfide, yeah, you will see that, yeah, sorry. I guess I will want to put into the fourth way, right? Because also aluminum important because that people originally want to use. You can see more stability also all very poor. And actually, there's people started using arsenic and antimony. Yeah, you can sort of see that actually after on this end, right? And alkaline metal is sort of in the middle, and the lake condition metal sort of shows best. Okay, so yeah, so this sort of gives indication of what's good and bad. And if you look at the sodium, right, if you want to work on a sodium electrolyte, this also shows a trend, you know, what's good and what's bad. Yeah, so that can guide your decision. Okay, so with the moisture stability, right, that's one thing we want, and also we want the reduction stability, right, which is the stability in the lithium metal. So then with that, we can actually plot both, right, on the two axes. So this helps us to understand, you know, how we pick a material that, right, we have multiple stability design, right? So for example, we want lithium metal stability. Okay, on this scale, I also call the reaction energy, right? So basically, the right is better, right? On the right is the positive, and the water stability higher is better, right? You know, it's less driving force. Okay, but basically, for the lithium, I guess the thing you see is that this rare earth here, right? We are sort of having a fast metal stability, right, as I showed. And you know, more stability, I would say, sort of decent, right? Not molten. Okay, so we also do that for the sodium because it's also interesting developing sodium battery, right? Sodium, I would say, is actually you do have a lot of material that are sodium metal stable. Okay, so this possibly because sodium are not as reducing as lithium. So that may be a good news for sodium solid state, right? If you want to do metals, you know, I mean, sodium metal has all the issues. Yeah, but on the stability regard, yeah, you do have better choices. And another thing is that chloride for electrolyte, right, which I mentioned is the new material. You know, invented as Panasonic back 4 years ago, and yeah, we can also evaluate that. Then for chloride, I guess the good news is you can see the moisture stability is much better, right? And among them, you know, you can see the lithium actually from calculation shows the best. And actually, this is the you know, work by one of our collaborators, Andy Stern, the Western Ontario. So yeah, so this is basically what we find is also, you know, one of the best moisture stable you know, chloride material. I guess you can see that, you know, even with they put a pretty high humidity, right, 30% humidity, right? You know, it's not as humid as our summer, right, in Maryland or in New York City, but that's pretty high, right? You can still see the conductivity degradation is very unique. Yeah, so that's also kind of like why the chloride has attracted a lot of attention in the solid state community, right? So it's actually also very good for lithium production. But I guess the bad news is that also they are not as stable as lithium metal, right? So I guess here you will see that, right? You know, for each class of materials, you always have this trade-off, you know, is that you want so many property, right, in your materials, so you can make your engineering easier and cheaper, but you can never achieve that, right? So I guess having a computation, if you have a guidance of that, is good, you know, because at least you have math to see like where to look for, right, you know, or like what the limit could be, right? So yes, I would say that's kind of you know, what I'm trying to show you and convince you, and hopefully it's useful to you down the line in the future. Okay, so I guess the conclusion, I probably won't read this through, but basically just, you know, show you some of our examples of how we use, right, first principle calculation and machine learning, you know, to provide materials understanding, enable new material design, yeah, and uncover physical insight, right, and also hope to convince you that computation approach using database, you know, can indeed help you provide a lot of crucial information you need when you're selecting materials or design or improving materials. And certainly, you know, we have multiple success, right? That we really did demonstrate things like we really first predict in computation and later confirm by experiments. Okay, so with that, I would like to confirm thank my group and the students with the hard work. We have a relatively small group there, and our collaborators we had over the years, and also funding support from the Alliance and will be happy to take any questions. Sorry about the typing issue. So I have now animation doesn't work.
I have to say sorry.
Otherwise, probably even easier for the students.
But it was still a great pedagogical presentation and this nice. So, any questions? I can also get this started. So, what do you think about the importance of the mechanical properties of the solid electrolyte, especially its interface? And do you think there's hope to get this kind of information from atomistic decision?
Yeah, I think the mechanical property, yeah, I guess there's a number of things. Like one thing is whether it's computable. I guess for us is that whether we have a reliable method to evaluate that. So certainly for all the elastic property, right, elastic constant, Young's modulus, so we can do very well, right? Like I mean, yeah, depends on how accurate you want to be, but we can do pretty well. But if you look at like more plastic property, right, then usually that is depends on either microstructure or other type of mechanism, which you may correlate with the elastic constant, right? But there's something you need to worry about. So I guess that's the first thing is that, right, whether they are really computable, right? And the second thing is that, yeah, it's certainly in the battery is important, right? Because I think mechanical important in two ways. One is in the cell manufacturing, right? Like the sulfide and also the chloride are very soft. So actually, it's very easy to assemble those solid state battery. You actually just put material, you just press them. You can just cold press, and then the battery cells start working. Yeah, another thing is the volume expansion, right? This cycle, the cathode change volume, so they may have some mechanical breakdown there. Then you may need some mechanical reform. Yeah, so certainly mechanical properties are important, right? It's just yeah, whether you're computable, right? If you can solve that problem, that's a good research direction.
Just to be clear about what makes it uncomputable is that you're talking about grain boundaries and things that are too big for your box, for your simulation.
Yes, sort of. Yeah, if it's a microstructure dependent, then right, then at least it's that's not accessible by DFT part of research. Yeah, actually, I have some other study I haven't shown, but basically we can do this sort of called a large scale molecular dynamic simulation, which we can go 100 nanometers, for example. Then in that case, we can have some grain boundary, right? And I actually used that before to study some plasticity and ductility issue. Yeah, but I guess it's also like you have time scale issue and other things. Yeah, but I guess that's more for like detailed mechanistic study, right? Like if you want the materials design discovery, why this first principle method works so well, because it's based on quantum mechanics, and you can readily apply it into any materials, right? Any structure, any chemistry, they just work. Yes.
The question here, Yuan.
Excellent talk. I have two questions. The first one is about the first part. So we know the conductivity is proportional to, it's related to the energy barrier, but it's also proportional to the vibrational frequency. So we will have multiple ions move together. Will that also affect the vibrational frequency? Second question is, you show the nitride has good stability with lithium metal. So what are the disadvantages of nitride? Because we haven't seen much studies on that.
Okay, yeah, very excellent question. So so for the first part, vibration certainly is relevant because I think Professor Xiaohong published a series paper, right? But usually vibration, right? Like for the chemical engineers to be there, right? So like the frequency, right? Like they vibrate there. So they are usually also correlated with a number of things, right? Like bond strength, so you cross different ion chemistry, right? That can change. Yeah, so certainly just by looking at the vibration frequency, you would capture that trend, right? That's for sure, right? And bond strength and on the large scale, they do correlate this barrier. On that regard, I also want to say that for the lithium, it's actually also matters. The reason is that actually that's a part I didn't show, but basically usually with this material, you will have this lithium side that becomes very flat in certain region, you know. So then with that, you will get some, how to say, anharmonic kind of vibration frequency. Actually, I think it's also, you know, a number of studies have reviewed that. Yeah, so certainly if you look at vibration frequency, there's a lot of indication, right, of, you know, whether they're being conductivity or not. Yeah, so that's an excellent question. For your second question, nitride, yeah, very good question. I think the nitride, I guess, you know, I guess one thing obvious you can see from the map is that the cathode stability is very, very poor, right? You know, so your cathode voltage, right, is way up here, but the cathode stability is very poor, right? So then with that, you cannot use as a full solid electrolyte, right? You can only use as anode coating, right? You can add coating or anode protection, right? And another thing is that this thing, yeah, that's the most stability is also very poor. Air stability is very poor, so that's also an issue. You know, it's probably also one of the first. Yeah. So yeah. So there's a lot of actually 70s. There's a lot of early research on lithium nitride, right? Without the metal, you know. Yeah, but I think it is also going to go. Yeah. But now it's still used as the anode.
Right, so this is more related to the concentrated migration. So for any given structure of your solid electrolyte, you can just dope it and probably increase your conductivity. Is that often done? And number two, if you keep increasing your lithium content, you will at least at some point there won't be conduction at all, right? So what is that optimal point?
Yeah, exactly. That's a very good question. So I would say usually, right, you take how you say a crystalline material and you dope it. Usually it's improved later, you know, because the reason is that they have no carrier, right? They sort of like either have no, if it's concerted, right? They don't have this interstitial, because you know, vacancy mechanism, they don't have vacancy. So usually if you dope a little bit, it's increased, right? But there's an extent to which there's a maximum, you know. Usually there are two kind of mechanisms. One is like you cannot dope too much, you know. So right, you can only dope so much, like beyond that point, right, the phase is not pure or like segregate out, you know. So that's often limited because you have a bad phase segregate out, right? It's pure, you can do this significantly. Sometimes you do reach it, it's because you know too much lithium is not good, right? So then you have to look at the detailed diffusion mechanism. So that's also possible. Like, you know, there's certain range you can deposit a whole completion range, but you have the optimum somewhere, like you go over to it and start dropping. And that's really up to the specific diffusion mechanism. Yeah.
Final question? Yeah, maybe.
You mentioned about like the chloride has a good moisture stability. I wonder if we are using the lithium metal as the anode, like we want to avoid the moisture. So why that the moisture stability important here?
Oh, okay. It's really for the manufacturing process. You know, like when you make the material and assemble the cell, basically the sulfide is just so bad that, you know, like very trace moisture will damage it, right? So yeah, chloride is very good in that regard. Another thing, so that's one thing, right? Like that's why it's relevant. It's more like on the manufacturing sort of processing side, right? Another thing is that people also want to do solution-based processing, but that goes into some technical details. Is that your cathode is still a composite. You know, you mix the cathode material, right? The active material, right? You have some electron conducting pathway, and also ion conducting pathway. To mix that very nicely, to have a good materials utilization, usually the solution processing does better. You know, so that's another motivation that, you know, if you have good moisture stability, you can do some solution-based processing. Yeah, to make the cathode composite. Yeah, but certainly that's an issue, right? Not in the liquid electrolyte, because you just drop in liquid electrolyte, it automatically goes in, right? Here you have mixing three solid, and you want to have optimal metal microstructure, right? So yeah.